Yeah, this work, I'd like to thank KT Boundary LLC for partially funding this work. Dominique Surel is my advisor. I'm Debra Overberg, and Rhonda Cleaver is the biologist in the group. So I'm an electrical engineer, and that's my background. And currently my day job is as an energy healer. So how do I turn this? Through this?
That'll work, yep.
Okay. So what I'm interested in is the difference between what is electromagnetism and chi, and I've been very interested in Margaret Moga's work. It's, following that magnetism and how do we do it, but I'm also interested in the measurement of that. And she mentioned Bill Tiller's work with the two dual level mechanisms, that there's the electromagnetism on one level and perhaps something on another level. And that's what I'm looking at, is electromagnetism versus chi or prana. And what I'm trying to do with this is there a scientific, definition or way to partially define what is that energy, the science of chi? Can we define that not just as vitality or life force energy, but as something else? And that's where I think the neutrinos come in. That the neutrinos could be that energy portion of chi. And then we'll relate it that could answer some of these questions with quantum biology and the quantum phenomenon that they're starting to see as a new field, an emerging field. So looking at this idea of chi, I like this picture from 1925 that coming from the sun, they separated out that there is something they called phohot, or electricity, heat, light, and sound coming from the sun that is distinct from prana. And that is very similar to what we'll see with neutrinos. But what I also found was that as I switched from being an electrical engineer to an energy worker, they're using the same language. It's the same language of energy, frequency, resonance, coherence, and yet it didn't feel like they're talking about the same thing. That are they talking about two different things? That is that chi coming in and then being part of our biology, and then we have the electromagnetic response. I like our Bill Bankston. Everybody knows Bill. He always used to say, is there any energy in energy medicine? And some of that is because of this low-level signals that we're doing. Margaret mentioned the squid for that, with measuring the squid magnetometer, measuring our field out 2 to 3 feet. Well, that's like an MRI machine. That's a big, expensive machine. The Q stands for quantum. So we're measuring very low-level signals out there. We're not measuring a big signal, and yet we can see a big signal out there. And biologist James Oschman, who's spoken at the SSC, there's energy running all over biology. We know there's a lot of vitality. There's a lot of energy going out there. So what is it? Energy of what? What is being measured? And I wonder if we could add in that idea of a neutrino energy, which is what they were originally postulated to do, is add energy, the missing energy. So same here. Chantal had asked, thank you, had asked, where did I come from? First introduced to this idea was in Brazil, Indigenous Day in Brazil. The various speakers here, this was one of the US senators, one of the Kayapo Indians there. Well, they had this amazing heart energy that I felt during this entire day. The next day, I'm walking down the city back to the hotel, I feel that heart energy. A block later, I turn the corner and there's a group of the Kayapo having lunch. I'm going, oh my God. I felt that half a block away. So that's where you go, that did not feel electromagnetic to me. It did not have anything. It didn't have the 1 over R squared resonance, I mean, it did not, it was a different animal. So I do think they influence each other, that the electromagnetism and chi, we see that. It goes both ways. And so that's the correlation I'm looking for. Okay. So I love the picture of the baby that we had before, where they're full of chi. And that growth, repair, healing, this is where I think the neutrinos can play that biggest part. I think I mentioned this. Okay, so what's a neutrino? Neutrino is known as the ghost particle, and it's not a particle of not in the periodic table of the elements. It's part of our standard model of particle physics. This is the newer version. Some people might have seen the square version. The Higgs boson is known as the God particle. That's not the neutrino. It's surrounded by bosons. We're going to talk about bosons today, and Bose-Einstein condensates in particular. Out here are fermions, the quarks that make up protons and neutrons. We've got our group of electrons and our group of neutrinos. Neutrinos is the ghost particle, which means it's got a subtle energy associated with it. Now, neutrinos do come from the sun. We've got 70 million neutrinos per centimeter squared per second. The centimeter squared is the size of your thumbnail. So not only do we have those cosmic snowballs, the cosmic comets raining down on us, but we also have 70 million, a whole bunch of neutrinos. Let's see. What I was going to say too is though those cosmic snowballs and the photons coming from the sun are blocked by the Earth, but the neutrinos go through the Earth. And this has been shown with the super K that we've got a bunch of neutrinos on one end and we've got the same amount coming on the other end. So at night, the invisible light, the transparent light from the neutrinos comes up from the bottom of our feet, you know, instead of raining down on us, on our heads. Now, the problem is the old paradigm view, and we all know about our paradigms here, is that a neutrino will pass through a light-year-long column of lead with only a 50-50 chance of interacting. And we'll get back to that, but we're going to point out here that that is a particle interaction. This is the billiard ball idea, that a neutrino must hit directly a quark. But those quarks are itty-bitty little pieces in a vast cavernous cave of a proton. And they're very far apart, very rare, very small cross-section is what they call it. So we're going to look at how we measure a ghost, because we're looking at measurement here and test equipment. How do we measure this? Well, what we do is the neutrino has an interaction, and then we measure a photon that is a result of that interaction, and then we infer that neutrino event. From Duke University, they call that a flash interaction. There are others. We're not going to talk about that today. So big, huge vats, big, huge vats. Big, huge vat of dry cleaning fluid is where the neutrino interaction takes place. Somewhere outside the vat is a photon detector. We measure it, we quantify it with the photon, and then infer the neutrino. Same with the super K. Here's a big vat of water, but the photon detectors are the actual quantifying. The neutrinos are unquantifiable. Same with the big ice cube. The neutrino event takes place in the ice. The photomultipliers detect. Now, starting in 2017, the new science is that there's also a wave interaction, a neutrino wave that hits a larger target area, a larger cross-section, and that, so this is a new one going from a particle to a wave interaction, has a larger cross-section. And what is significant about that is that in the accompanying paper, they said that this old paradigm has to switch. So not only are we going from this huge vat of equipment, we're going to go to smaller, we're going to see what it is, but that neutrino is going to pop out of that light year. It's going to be scattered by that wave interaction within a few days. It's not going to make it through the end of that column of lead. So here's the new system. Now we don't have those huge vats. We don't have a mile, quarter mile of ice. We're using a detector that's handheld detector, put it in a shielded enclosure, neutrino event here, detector here of a photon detector. So what does that mean for us? Well, first for some of the things in the Earth is that no longer do neutrinos only be thought to zip through everything, they can bounce around. So they can hit some atoms. They don't just have to zip right through. And even though the number of neutrinos before and after is the same, they don't have to take a straight line path. They will scatter. And what does that mean in terms of the biofield that we're talking about in chi? Is that anytime we measure a biophoton coming out of here, we will measure, it could be coming from a neutrino. And we really have no way of knowing that. Right now, there's no way to distinguish between where that biophoton is coming from. And a biophoton is measured just like any other photon. Whether that biophoton has information on it or not, we don't know. Or if it's tied to a neutrino, we don't know. Because what we're measuring is just the photon. So there could be. So what do the neutrino physicists think about neutrinos in biology? Well, I looked around. Basically, what I found was that they had this on their website at Fermi Labs in Illinois, that neutrinos will pass through your body without interacting with other particles in your body. They'll just zip right on through, just like they said, zip right on through. But this new wave interaction, they said, ask a neutrino physicist. I typed in and said, have you shown this? Have you demonstrated this? When have you measured, this result? And now on their website, they say the neutrinos pass harmlessly through your body. So they have taken into it. Now, we're trying to look at neutrinos in biologists, and what do the quantum biologists think about neutrinos? Nothing. It's not on their radar. If they talk to a physicist, if they talk to an engineer, they go neutrinos zip right on through. They don't do anything. Quantum biologists have plenty on their plate to think about, so they're totally ignored at this point. And that is my question: is can we bring these together? That's the maverick science that I'm talking about. Is can we bring these two ideas of neutrinos that show up as photons and related to the quantum biology? So quantum biology is filled with all the stuff we know about: quantum tunneling, quantum entanglement, superposition, biophotonics. I'm going to talk about the coherence part. A lot of people here have talked about coherence, creating order and structure in a system. And one of the big things that creates that coherence is it's like a Bose-Einstein condensate. How many people know what that is? Okay, we've got two. Superconductors. These are things that are originally projected to occur only at absolute 0 minus 273 degrees centigrade, 0 degrees Kelvin. And quasi-particles, we'll talk about those, part of that. So quantum biology shows up in these various forms, but in a big one we'll see is electron and proton transport. How do we move energy across the biology? It happens extremely efficiently, which could be useful for some of our energy harvesting devices. So the polarized molecules is one area where they think they might be quantum entangled, and long-range phenomena. So where does it show up in biology? So here I have, this is Wilson. Okay, Wilson here. He is a biological cell. He's got his DNA and his nucleus there is falling out. But in a biological cell, it has the membrane, the cell membrane, which Bruce Lipton talks about a lot, is made of the fat layer, the lipid layer. And this has an extremely high potential, 100,000 volts per centimeter electric field, because it's over a very narrow distance. So this is a huge electromagnetic field contained within this. And what I'm wondering is this a place where the neutrinos could be interacting with? Because that lipid bilevel is a liquid crystalline, just like the liquid scintillators of the neutrino detectors the neutrino physicists are using. And could that be? Now we have a huge target area. Now we have a cross-section that's very large that all those neutrinos coming from the sun day and night could interact with. So what does long-range coherence mean? Thank you. This is where this wave pattern here is much longer than the intervals of the individual particles or atoms. And back in 1968, this was discovered. Here's the Bose-Einstein condensate, where the individual bosons can occupy the same state at the same time, unlike fermions. So they can come together and create this field, thousands of particles, thousands of atoms together over a large geography. So this wave pattern is over a very large geography. And it's been just recent that room temperature boson condensates occur. It's been happening, they're finding it out. There was a new article today on something similar. 2010 is when this started to be coming about. Who would have thought that something that normally was predicted only at -274 would happen at room temperature? There's a lot of these. The difference then between Bose-Einstein condensates, lasers, et cetera, superfluidity, superconductivity. How do we tell the difference in a biological substance? Paired electrons, here's a good one where they show that these paired electrons, which allows you to get a boson out of a fermion so that we can create this large wave pattern in biology. This is the coherence that's found in biological systems, and it relates to this quantum entangled pairs. We won't go into that in so much detail, but it does relate to the coherence. A lot of times these pairs of two fermions to create a boson, they say it'll decohere. And I think adding the neutrinos to that system and that are quantum entangled could keep those systems from decohering and add to the coherence times of the systems. Now, just recently, May of this year was the first time that I've seen in the literature. I'll have to do some more literature searches coming on here, but that they directly tied the photosynthesis to the Bose-Einstein condensate problem. And this answers, how do you get that this was our wave pattern, this large geography of the fast energy transport possible, I think, by adding the neutrinos. So then it can be part of that light harvesting, energy harvesting, and harvesting of the invisible light of the neutrinos would be part of this, part of that energy transfer. So we talked about the particle and the wave, that the particle to particle, our billiard ball model. The wave has been validated and confirmed since 2017. I'm also suggesting a bioneutrino field where that is tied to biology and the electromagnetic field, that they're interacted, that this is part of a larger one. This is also in agreement with some of the Italian physicists. They work with the quantum field theory tied into the water of Jerry Pollack. Random water, bulk water. This is the polarized particles, the quasi-particles we were talking about. Water makes a boson as well. Here's two water particles, H2O, random. What happens is they're coherent, they're in sync, they're in that long-range pattern that we saw. Okay, and they also predicted we need an external energy source, which I think is the neutrinos. Or I'm questioning, could it be the neutrinos? So we have our biofield and our nesting of the forces with our nuclear force, electromagnetic force, and the bioneutrino force as this larger field. There are new tools that are starting to come about for the quantum field. I like Clarice's summary. Quantum biology might be where microscopic quantum physics upscales into the macroscopic day-to-day world. So neutrinos are real. They're not a made-up event, not a made-up particle. They're available all the time, day and night. A universal source of energy that could be added to that, creating coherence and order that they're finding is like these superconductors, Bose-Einstein condensates. and that might be potentially, is that the question? That's the question. Is it our life force? Part of our long or part of front? And that's what I want to know.